All right, so let's get started with the next exciting session of POPL'23. This session is it's titled Algorithmic Verification, although I'd like to give it a larger title called Algorithmic and Complexity Theoretic Aspects in Testing and Verification. There is a very nice theme to all the three talks today, which is language reachability. Language reachability is essentially the problem, is the following problem. You're given a directed graph where the edges are labeled, and you're supposed to check whether there is a path from S to T, which is labeled using a word in the language that you're given. And all the three talks sort of give a very nice overview of different aspects of this problem. This problem has been gaining a lot of interest in the past 4 or 5 years in POPL, PLDI, because there are a lot of applications in program analysis as well. So with that, I think I'll give the I'll let Shaleen Deep from Microsoft Gray Systems Lab to talk about fine-grained complexity results for this problem.
Okay, I'm audible, right? Great. Okay, thank you, Mang. Hi, everyone. Thank you for coming to my talk. My name is Shaleen, and I'm a research scientist at Microsoft Gray Systems Lab, where we work on all things database. And today I will talk to you about some of the recent work that we've been doing in understanding the fine-grained complexity of reachability problems. So let's get started. So as Umang said, static analysis problems are frequently expressed via label-directed graphs. And in the graph, the problem is to find all S-T vertex pairs, such that if you look at the labeled path from S to T, and if you look at the labels and see what word is formed by those labels, it belongs to a specific language L. And L could be many different languages, but when L is a CFG, the problem is known as CFL reachability. And CFL reachability has very wide applications in a lot of areas. It's used in interprocedural data flow analysis, program slicing, shape analysis, Anderson's analysis for pointers. It's also used in databases where we use it for social media analytics and so on and so forth. So since this is such a common operation, it is important to understand how fast we can solve this particular problem. And in particular, what are the time complexity bounds for solving this CFL reachability problem? So CFL reachability is of great interest, not just to the PL community, but also to the database community, where I come from. And there's a huge amount of work that has been done in understanding the analysis of labeled graphs. A lot of this work was done in the early 2000s in the context of XML databases. Evaluation of regular path languages and its extension is still a very active area of research in database community. And document parsing, document spanners, all of these touch on core aspects of CFL reachability. And of course, we have data log evaluation, which has very close connections to this particular problem. So let me touch upon some of the work that is directly relevant to the work that I'm presenting today. So the first work that I would like to highlight is the seminal paper by Yannakakis that appeared in PODS in 1990. And Yannakakis showed that CFL reachability in general, it can be solved in n cube time for a specific language. And here n is the number of vertices in the graph. And follow-up work has showed that the same problem can be done in slightly subcubic time. So you can go from n cubed to n cubed over log n, getting a logarithmic improvement. And if you want to go truly subcubic, Fisher and Meyer showed that for using matrix multiplication, for regular languages, you can get an n to the omega algorithm. So omega here is the exponent for matrix multiplication, and the best value is, I think, 2.31. So if you look at these results, one observation here is that if you truly want to go subcubic, you have to use fast matrix multiplication. And this is not a coincidence. It was shown by Abud and others that there is no truly subcubic combinatorial algorithm for CFL reachability, which basically means that if you want to go subcubic, you have to use fast matrix multiplication. So what does combinatorial algorithm mean? So there is no formal definition for combinatorial algorithms, but it is usually meant to say that the constant in the big O notation for whatever algorithm you're using is not too large, which basically means it's feasibly implementable in practice. And essentially what this means is you should not use fast matrix multiplication because it's not very practical. So if you look at the results that we have so far, these existing results, they do not really tell us about how to evaluate CFL reachability for a specific language L. And that is the main motivating theme of this work. Can we get more fine-grained results for specific CFGs? So this is the overall broad question that we are trying to answer. So given a specific CFGL, can we identify the exact expression of the running time as a function of the input size? So we consider two variants of CFL reachability problem. The first variant is the all pairs, which is you have to produce all pairs that are reachable, and they also satisfy the labeled path property. And the second problem that we're interested in is the on-demand problem. So in this particular problem, you're given your vertices S and T, and your goal is to check that there is a path from S to T, and it satisfies the labeled property that we were talking about before. And I will also pay special attention to Dyke K languages, which is the set of all well-matched parentheses, and the parentheses are of K different types. So since we are going to look at the fine-grained complexity of these problems, we need to get some fine-grained complexity-based conjectures, which are relatively well established. So in this work, we rely on 4 complexity conjectures. The first conjecture is Boolean matrix multiplication, which says that there is no subcubic combinatorial algorithm for multiplying two n cross n matrices. The second conjecture is the three-sum hypothesis, which says that there is no subquadratic algorithm to identify whether there are 3 integers that sum to 0. The third conjecture is the combinatorial K-clique problem, where we say that there is no n to the k minus epsilon algorithm to detect a K-clique in a graph. And here the value of k must be greater than or equal to 3. And when the value of k is exactly equal to 3, this becomes the famous triangle problem. And the last conjecture that we will rely on is the all pairs shortest path. And this conjecture says that there is no subcubic algorithm for the all pairs shortest path problem. So another interesting thing that I would like to bring to your attention is we are not interested only in finding the running times in terms of n, which is the number of vertices, but also in m, which is the number of edges of your graph. And this is a very common setting in the database world, where we want to find the complexities and the running times in terms of the size of the database. And the size of the database is m plus n, and m can be as large as n squared. But usually m is equal to n, which is basically the sparse graph setting. So we will also pay special attention to this particular setting to get some complexity result bounds, not only in terms of n, but also in terms of m. Okay, so let me highlight the specific contribution of our work. So the first result that we show is that for Dyke reachability problem, the all pairs reachability for Dyke 2, there does not exist an algorithm which is better than n to the 2.5 minus epsilon. And this is assuming the three-sum and the all pair shortest path conjectures. And the interesting thing about this result is that this lower bound holds even if you assume that you can use matrix multiplication. The second result that we have is all pair CFL reachability related. So here we show that there is an interesting CFG which has a running time of n to the omega plus 3 over 2. And why is this number interesting? This is interesting because this is between cubic, which we know is true for CFGs in general, and between n to the omega. So this is a grammar which falls somewhere in the middle. For the on-demand reachability problem, we characterize the fine-grained complexity for the dense and sparse graph settings. And finally, for Anderson's pointer analysis, we show that there is no subcubic algorithm in terms of m. So a prior work from POPL'23 showed that this lower bound also holds when with respect to n. So you cannot get a n to the 3 minus epsilon algorithm. We are strengthening it to say that you cannot get a m to the 3 minus epsilon algorithm. So in the interest of time, I will talk about the first 3 contributions, and I'll give you a flavor of some of the ideas and the key reductions that we use. So I'll talk about Dyke reachability, followed by all pair CFL reachability, both sparse and dense. Then we'll discuss the on-demand reachability. And finally, I'll talk about some future work and some interesting open problems that still remain. Okay, so let's start with dike reachability. So recall that the goal here is to show that the hardness for all pairs reachability problem for dike 2, we cannot do it better than n to the 2.5 minus epsilon algorithm. We cannot achieve that. So in order to do that, I will require the following problem called the AE mono triangle problem. And this says that given an n node graph where each edge E has a color associated with the edge, determine that for every edge, whether it participates in a monochromatic triangle or not. So for every edge, if there is a triangle, all three colors should be identical. So prior work has shown that this particular problem does not admit a better algorithm than the one shown here, unless both all pairs shortest path and threesome problem have better algorithms. So this is a pretty strong result. So in order to show you the reduction, let me set up some notation and background. So we will use the, for each edge, we will have an integer associated with it. And I will use the binary encoding of that integer and encode it using brackets. So in the encoding for E, I will use the open square bracket for bit 0 and open parenthesis for bit 1. And if we reverse that particular encoding, I will use a closed square bracket for 0 and close parenthesis to represent bit 1. So as an example, if E is the integer 3, the line graph for this particular encoding would look something like this, where you have the two square brackets representing 0, 0, and open brackets as 1, 1. And the reverse of that is just the reverse of this particular graph. So we will take these things and create a gadget. So in order to do that, I require also an operator that basically takes two line graphs and stitches them together. So in this particular example, I have taken the line graph for E, for the reverse of E, and I basically concatenated them. So how does the reduction work? So it works in the following way. I have my original vertex set V. I will create 5 copies of this particular vertex set, A, B, C, D, E. Each edge is assigned an integer I, and each color is assigned a distinct integer, which is m plus j. So we're basically assigning unique integers to all of these things. And then we do the following. So for each edge that is present in the graph, I will find the copy of u in A, I will find the copy of v in B, and then basically create a line graph over this particular edge. And then I will continue the same process. I will find the copy of u in B, copy of v in C, and attach this particular line graph here. And this continues. So we have 5 partitions here, so 4 different line graphs that will be attached. So what do we want to show here? So once we have done this encoding, I run my all pairs dike 2 algorithm on this. And suppose there is a path that goes from A to E. The key observation here is that because this is a dike 2 word, that means these brackets are well balanced. And because these brackets are well balanced, that basically forces the first color C1 to be equal to C2, C2 must be equal to C3, and the first and last edges must be identical. And this is true because we have encoded the integers as binaries, so the balancing property does the work for us. And the reverse direction of this particular reduction is straightforward. So that's the key idea. So if all pairs dike 2 was an easy problem to solve, we would get a better algorithm from AE mono, which contradicts the APSP and threesome. So that's the first result I highlight for this part. In the paper, we have more reductions for all pairs for dike 1, and we highlight basically what are the open problems and how you can use similar ideas to get those results. So let me move on to all pairs CFL reachability. So in this particular part, I will highlight the result of something that we call as join-inducing CFGs. So what is a join-inducing CFG? So it is a join-inducing CFG is a grammar if it produces a string of length at least 2. And if this is not the case, then we say that this grammar is join-free. And the interesting thing about these CFGs is that in linear time in the size of the grammar, we can check whether L is join-inducing or not. So our main result for these grammars is the following. So we can show that for any join inducing CFG, if all pairs on this grammar can be computed in Tn time, and this Tn has to be larger than n squared, then Boolean matrix multiplication can be solved in big O of Tn time. So how do we show this? So the key idea is that because this is a language that produces a string of length at least 2, so you have S1 and S2, I can take a matrix M1, assign a label S1 to all of the edges present there. I can take matrix M2, assign a label S2 there, and then if I can do matrix multiplication over here, because the grammar recognizes S1, S2, I will be able to get all of my output for Boolean matrix multiplication. And the second result that we show here is that if the grammar is join free, then all pairs on this particular grammar can actually be solved in linear time. So here is a summary of the results that we have in the paper. So for join free and join inducing, we already saw the results. If your grammar is join inducing and additionally it is linear, you can do slightly better. And for Dike 1 and Dike 2, we have the following results. So for Dike 1, we show that the lower bound is m squared and the upper bound is m cubed. So this is still not tight and this remains an open problem. But for Dike k, where your k is greater than or equal to 2, we have an essentially tight result. So the best you can do is m cubed as the upper bound, and we show that you cannot get a subcubic algorithm. Okay, so the next result I highlight is all pair CFL reachability. So for regular languages, it's already known that there is an n to the omega algorithm. And prior work has shown that for Dike 1, all pairs reachability, you can get n to the omega log squared n algorithm. So the question is, does there exist a non-regular CFG that admits a subcubic algorithm for all pairs reachability? And the answer is yes. So if you consider the following non-regular language, AIBJ, where the value of I is greater than or equal to j, it is generated by this following non-regular, non-linear grammar. We can show that this particular grammar, the all pairs reachability problem, can be solved in n to the omega plus 3 over 2 time. So what is the key insight here? So we do this using all pairs shortest path, all pairs longest path, and something known as existence dominance product, which says that if you're given two matrices A and B, you get an output matrix C such that Cij is 1 if and only if there exists a K such that A of Ik is greater than B of Kj. So let me quickly sketch the algorithm. So the first thing we do is take the graph. For all edges with label A, we set a weight of -1 and we compute all pairs shortest path. Then we do the same thing for B, but we set a weight of 1 and compute the all pairs shortest path again. And then finally, once we get these matrices, we are doing an existence dominance product over here. The first two steps can be solved in n to the omega plus 3 over 2 time from a well-known algorithm. And it turns out that the existence dominance product is also something that you can do in the same amount of time. So the key insight here is the first step is basically doing all pairs longest path because we have set the weight as -1. And if you try to find the shortest path over -1, you're basically finding the longest path between two different points. Okay, so let me go on to the third part and highlight some results on the on-demand reachability problem. So as I mentioned before, the result from Yanaka case in PODS 1990 showed that for on-demand regular languages, you can already do this in linear time. So this is big O of m, and because m can be as large as n squared, if you have a Cartesian product, if you look at the complexity in terms of n, this is quadratic there. So the question here is then what happens for non-regular CFGs? And our main result is the following. So we can show that using the combinatorial K-clique hypothesis, the on-demand problem cannot be solved in subquadratic time in terms of m for the following four grammars. So the first grammar is Dike K for any k greater than or equal to 1, the language AIBI, and you have a string S in the middle, strings over A and B, where the number of A's and B's are equal, and finally palindrome strings of even or odd length, which have at least two symbols. So let me quickly sketch the reduction for the first part. So we use the K-cycle detection hypothesis for this particular reduction, which says the following. So assuming the combinatorial K-clique hypothesis, for any epsilon greater than 0, there exists a K-partite graph where finding a K-cycle requires quadratic time. And the interesting thing about this particular conjecture is that the edges are only between partitions, which is right next to it in the front and behind. So P2 has edges between P1 and P3, P3 has edges with P2 and P4, and PK has edges with PK minus 1, and then it wraps around to the first partition. So let me quickly sketch the reduction. We take the input graph between P1 to PK. We create a copy of the first partition P1, and the red edge that you saw on over here is basically encoded here. So all the edges between PK and P1 are inserted between PK and the copy of P1. Then we add the following edges. So there is an edge added from U to the first vertex in P1, a vertex from V to the first vertex in the copy of P1. For the first k over 2 edges, we add an open bracket. For the last k over 2 edges, we add a closed bracket. So we are trying to balance these because we'll form a Dyke word. Then for all of the edges that we introduced in P1 and copy of P1, we again add open brackets and closed brackets. And finally, between the edges of U to the first and the last one, we have an open and closed bracket. And now we run the on-demand algorithm for Dyke 1 and try to find a path between U and V. So the key observation here is that if you find a path from U to V, these brackets will be balanced. And the second important property that we want is that whatever vertex is used in P1, because these brackets are balanced, you will choose the same vertex in the copy of P1, which basically means that because these are copies of each other, you will find a K cycle in this particular graph. So let me summarize the results for on-demand CFL reachability. For Dyke K when K is greater than or equal to 1, in terms of n, we have a cubic upper bound, and we show that you cannot do better than this. Similarly, for AIBI, we can show the same result. And in terms of m, we have the following results. Let me just highlight the last two rows. For Dyke K where K is greater than or equal to 2, we have a tight result. But for Dyke K where K is equal to 1, this is still an open problem. So let me highlight the last set of results that I have on undecidability. So we have two different results where we show that assuming the combinatorial K-clique conjecture, depending on whether you have the all players problem or the on-demand problem, it is undecidable whether a particular CFG reachability problem can be solved in m to the c time, and the c belongs to these two different ranges, depending on which particular setting you are in. And how do we show these undecidability results? So this is basically an application of Grayback's theorem. And Grayback's theorem says that if there is a non-trivial property for a CFL problem, that is true for all regular languages, and it needs to be preserved under the right quotient. So this is a special property that you require for your languages. Then C is basically undecidable for the class of CFLs. Okay, so let me quickly summarize a few future work and important open problems that still remain. So the first one is the complexity for Dyke 1 still is unsolved. And the main reason is because in all of our reductions, we are using encoding of integers, which requires at least 2 brackets. We don't really know how to encode those using Dyke 1. The second interesting problem is, so in this paper, we had another example of a CFG where you have a running time which is between quadratic and cubic. So it seems like there is something more that is happening here. So can we characterize what this class of CFG is? Is there a rewriting to a different class? And in the same spirit, can we find out which particular CFGs benefit from matrix multiplication and by how much? So one of the goals that we had when we started this project was to look at data log programs. And the goal was to find whether we can get tight upper bounds for data log evaluation. And we answered this question positively, partially. So it turns out we can use all of the notions from joint processing and query widths in the database community. and use in the data log world, because a data log query is basically a join query, but you need to do some extra work to find out what the width of these things is. And finally, for all the practitioners, how can we use matrix multiplication to help in reality? And this is not a far-fetched question, because in the database community, it has been shown that you can use matrix multiplication to speed up join processing by orders of magnitude. So I believe something similar can also be done for evaluating CFGs and important problems in the PL community for these problems. So with that, I will conclude and we can take questions.
Let's take one quick question. Yes, so we have, yeah.
Hi, thanks for the nice talk. I'm curious if you have any results about incremental reachability, where you have maybe one edit. You edit something, you modify it, and then do you have any lower bounds?
Yes, we don't have in this paper because we only deal with the static setting, but there is a paper that appeared in ICDT 2021 that talks about the reachability for dynamic settings. And they have results where you can use the fine-grained complexity conjectures for dynamic query processing and show lower bounds and upper bounds for regular languages, linear, non-linear, and different type of CFGs. So that's exactly the setting that I guess you're asking about.